This is Euler's method. In German, EU is pronounced oi, so this is not Euler's method, like Euler, anyone? It's Euler, like someone who digs for oil. So for this method, this is about estimating solutions, just like slope fields was. Yesterday when you were doing slope fields, you had to kind of sketch where the solution would go, and you might have felt like it was a little bit arbitrary. It's not. You're allowing the slope field to guide your pen, but it feels like you're not going to be right on. Euler's method gives you an algorithm for estimating solutions. This picture of Euler kind of blows me away because he had like 14 children or something, and I mean, he's hot, but 14? All right. So in order to use Euler's method, you would need a differential equation. So you'll be given a differential equation, and you'll also be given an initial condition. So here the differential equation is x plus y, and the initial condition is that at 2, we know that the y coordinate is 0. And then you'll have to approximate the value of the function at a different point. So here's our problem, and it's the exact same problem. I'm just going to make a table and step through the table until I get to the desired value of x. So I'm going to make a table. I'm going to start with x comma y as my ordered pair. That's where I'm starting. And then in my table, I will also have a little tiny change in x. And I will have a dy dx, which is specific to whatever point I'm at, because as I move, just like with the slope field, as I move along with my x and y coordinates, that's going to change my slope. And then I'm going to have a change in y. And the way you figure out change in y is you multiply delta x times dy dx, and I'll kind of like if you have dy dx times delta x, you multiply and kind of the dx's cancel, and so you kind of get delta y. It's a little sloppy because we have a mix of deltas and d's. We're not going to have a dy dx. I mean, we're not going to use infinitely tiny steps because this is going to be an algorithm for estimating, and so that's why we have kind of a mix of deltas and d's. The dy dx would be ideally what the slope is, but we will be taking steps that will involve not an infinitely small step. All right, so we start at the point 2 comma 0. Our delta x is going to be 0.2. Dy dx is going to be x plus y. So for this one, it would be 2. And our delta y would be 2 times 0.2, or 0.4. That means that our next point, well, we're changing x by 0.2, so our next point would be 2.2, comma 0.4. Our delta x is still going to be 0.2. That's not going to change ever. Our dy dx now is going to be 2.6 because we add x plus y. Our delta y would be 0. What is that, 52? And so our new point would be 2.4 and 0.92 because we add 0.52 to 0.4. Our delta x would still be 0.2. Our new dy dx would be these two things added together, which would be 3.32. And our delta y would be 0.664. And so our final point would be 2.6. And we would add these two together. So we'd have, whoa, I'm going to write it down. 1.564. And so that means that our estimate for f of 2.6, oops, I wrote that wrong, f of 2.6, our estimate would be about 1.564. I'm going to show you I'll show you visually what we did when we did Euler's method. What we did was we started at a value and then we took a little step. We assumed that we had a straight line slope for that jump. We don't have a straight line connecting those two dots, but we're making the assumption that it's going to be a straight line as we connect each of these dots. So it's not perfect, because we're assuming that the slope will be straight. It's not straight. We don't have straight line segments joining our curve, but it's a way of estimating. All right, so we're going to do the same thing. But I want to point out that it's not the same slope each time. Like this starts off less steep and gets more steep as we get further out. And so we are adjusting our slope at each step. So it's a dot to dot, not just drawing a straight line and using that straight line once as the slope, like we did when we used a tangent line to make an estimate. When we did linearization, we were just drawing one straight line. And now that we're using Euler's method, we're going to draw like kind of a dot to dot pattern, adjusting our slope as we go. All right, I'm going to make this a little more manageable. If you saw that last slide for 1 second, it said make 5 steps. I'm going to have you make 2 steps. And I would actually really strongly recommend that you pause the video at this point and try making the table yourself. And as you're making the table, don't round ever. So store values on your calculator so you don't have to round. And work on figuring out what f of 1 would be using 2 steps. So pause here, please. Try it, and then you can restart the video after you've tried it. Here's my table so you can check your answer. I started at 2, 3. My delta x, because I'm taking 2 steps and I'm going from 2 to 1, is going to be negative 0.5. When I do my dy dx part of the table, I'm taking 2 times my x coordinate minus my y coordinate. So my delta dy dx is 1 for the first step, because 2 times 2 is 4, minus 3 is 1. And then I multiply these two together to get delta y, so I have negative 0.5. And then my new point is found by adding delta x and delta y to my coordinates. Since those are negative, my coordinates are getting smaller. And then my estimate would be that f of 1 is approximately equal to 2.25. Just to emphasize, Euler's method is an approximation. It's not exact. And the reason it's not exact is because your curve is always constantly changing, but we're taking a snapshot of what the slope is at a given point. I want to emphasize that if your curve, let's say your curve is concave up, if you're using Euler's method, your dot to dot is going to be slightly below the curve, because each of those tangent lines lies below the curve. So if you have a concave up curve, so if your second derivative is positive, then Euler's method is going to be an under approximation, because your tangent lines will lie below the curve. But if you have a concave down curve, then your tangent lines would lie above the curve. And so as you're using those tangent lines to estimate the value of your function, your tangent lines would be a little bit too big. So it would be an over approximation. All right, that is Euler's method.